So we talked about the Darcy's equation, right? Q was the flow rate, K was the permeability, A was the cross-sectional area of the rock, mu was the viscosity of the fluid, which is the resistance of fluid to move, and this was the pressure drop across the core sample. So if you have a core sample like this, and you are passing basically a fluid through that core sample, and there is a pressure drop, which we show it with dP. Pressure 1 is here, pressure 2 is here, and there is a pressure gradient. It means that when you have flow in this direction, P1 is greater than P2. And this is the cross-sectional area perpendicular to the flow. So that's A in that equation. Viscosity, of course, is the resistance of the fluid to move, and then the length of the core sample, that is L, right? So what do we define? How do we define the permeability? In the laboratory, this is one of the equations that we use to measure the permeability. So this is an example, for example, here, right? And you see that the viscosity 1 centipoise, which is for water, and there is a permeability which we want to measure it. So let's say you have a core sample, you take it to the laboratory, right? And you inject water passing through that core sample, and you apply a pressure gradient of 1 atmosphere, right? So, and the cross-sectional area, let's say, is 1 centimeter square. The Q is 1 cubic centimeter per second. If you do that and put it into that equation, you get a permeability equal to 1 Darcy, right? And that is basically the definition of the 1 Darcy permeability. So Darcy is basically another unit that we are using, but I think I mentioned that the actual unit of the Darcy's the permeability is centimeter square when you use this equation. Please also be careful about the units that you are using for Darcy's equation. So if you use basically atmosphere for pressure, centimeter for length, centipoise for viscosity, centimeter square for cross-sectional area, Darcy's for permeability, and cubic centimeter per second, this is the right set of units to use for this equation. We will talk about other types of units, field units, that we usually use in petroleum engineering, but if you want to use this equation, please make sure you have these units that you're using. So in fact, Darcy, you can convert Darcy to the centimeter square, or centimeter squares to the Darcy's unit, which is basically the actual unit of permeability. So K in that equation is called absolute permeability, and absolute permeability is measured when you saturate a core 100% with one fluid, right? So that's the definition of absolute permeability and how you measure it in the laboratory. So what you do is first you saturate your core 100% with let's say water, usually a single liquid, and then what you do is you inject then that liquid again into the core sample with those conditions of 1 atmosphere, pressure gradient, whatever basically number you use for the Darcy's equation. Then you can calculate the permeability, right? And that permeability is called absolute permeability. So 100% saturation means that you are filling all the pores with that liquid. So you don't want to have any pores that have other fluids or air in it, or such that, right? So it could be oil or it could be water that you use for absolute permeability, but usually what we do is we use water. But when they report the absolute permeability measure, they also report what liquid they have used to measure this absolute permeability in the laboratory. So when you have basically these fluids separately injected, right, you calculate what absolute permeability, right? Now let's say you're injecting two fluids together at the same time into the core sample. Then in that case each fluid will take some space from the core, right, depending on how easily that fluid will transmit through the rock, right, and also how much oil or how much water you are injecting through that core sample. Therefore, instead of absolute permeability in the Darcy's equation, for each of these liquids that we can write them here, QO is KOA P1 P2, mu oil length, Q water is KWA P1 minus P2 mu WL. You see that here we are using a different permeability. These permeabilities are called effective permeabilities. Effective permeability. So effective permeability is the actual permeability toward that specific fluid, right? Absolute permeability, since we only had one fluid, then that was it, right? That's the absolute permeability. But effective permeability, since there is another fluid, if you have more of water inside this core sample, then the oil can hardly flow here because it doesn't have enough space to flow, right? So you will have less production, you have less effective permeability, right? That's something that basically you need to be careful about when you calculate the permeability because you have a two-phase flow. So now here you have two-phase flow, and this effective permeability can be related to the absolute permeability through another parameter which we call it relative permeability. So relative permeability is the ratio of that effective permeability to the absolute permeability. So let's say your KRO is usually is basically less than 1, and let's say you have your effective permeability of oil to be 19 millidarcy, your absolute permeability 161, so it's 0.12. Your water permeability over absolute permeability 35 over 161, you get 0.22. So why is it important? You can just instead of KO here in this equation, write KRO multiplied by absolute permeability, right? Instead of KW, write KRW multiplied by absolute permeability. And this KR is relative permeability, which can be measured in the laboratory. So you can measure the relative permeability in the laboratory. Depending on, it's a function of the saturation. As you can see, this is a typical relative permeability curve. You will learn about this much more in the next semester, but just to introduce you to the concept, usually you get two curves like that, one for water, one for oil. The x-axis is your water saturation, and the y-axis is the value of relative permeability. Now, a trend that you can observe is that a couple of things that you can get from this curve. So first, look at how relative permeability of water is changing as water saturation increases. So water saturation increases in this direction, right? And as you go into that direction, you see that the value of relative permeability also increases. So the higher the water saturation, the higher the relative permeability of the water. On the other hand, if you increase the water saturation again is the percentage fraction of pore space which is filled with water, right? Oil saturation is the fraction of rock that is filled with oil, right? So if you increase the water saturation, that means you are dropping the amount of oil. Let me write this relationship for you. So SW, which is water saturation, that's how we show it, plus oil saturation, which is again the percentage of pore space that is filled with oil. If you have only these two fluids inside the rock, then the summation of these two will be equal to 1. Okay, so the higher the water saturation, the lower the oil saturation. And the definition of water saturation is volume of water inside the rock divided by pore volume. Oil saturation, volume of oil divided by pore volume. That's the definition. Okay, so we have this, right? And you can see that from this figure, as the water saturation increases, it means the oil saturation is dropping. the relative permeability of oil also drops. So the relative permeabilities both are functions of saturations, right? And at any point, let's say you have a rock that is at 60% saturation, right? You go here, you hit the curve, you read the value of relative permeability of oil, you go up, you hit the water relative permeability curve, you read the relative permeability of water, and that you use it in Darcy's equation here. Instead of basically KO, you write KRO. K absolute, you measured it also in the laboratory using 100% saturation of water, for example, right? And another thing is that there might be some saturations that you have some oil saturation or you have some water saturation. Let's say here 10%, right? Not exactly here, but here, let's say you have 10% water saturation, but you see still the relative permeability of water is 0. That amount of water is not enough for water to move, and that is called irreducible water saturation. So oil also same situation. You see at 20% oil saturation, from 0 oil to 20% oil saturations, the oil does not move. You see the relative permeability. If relative permeability is 0, then no fluid flow. That's the general rule. So if it's oil, oil will not flow. If it's water, water will not flow, right? Why it will not flow? Because look at the Darcy's equation. If KRO is 0, then then all these fraction will be 0, so QO is 0. If KRW is 0, it means the whole fraction is 0, QW is 0, right? So relative permeability, if it's 0, then there is no flow. And the concept of, again, relative permeability comes to the picture when you have multi-phase flow. If you have a single phase flow, which means you have only oil or you have only liquid water flowing, then we use the concept of absolute permeability. So I guess that's it for this video, and let me go over this. Well, we can do this example next, right? Let's do the example in the next video.